Hello and welcome to our video proof. My name is Tate Farmer, and along with my partner Jonathan Ramirez, we are going to explain Morley's trisector theorem. We hope you enjoy. First, we will go about proving some of the more simple theorems that will be used in this video. This way, when we use them later on, we can simply state them as fact. The first theorem that we're going to take a look at is that the sum of the interior angles of a triangle add up to 180 degrees, and we will prove this by constructing a triangle as shown. So now that we have our triangle, we can start labeling the vertices. So this first one we will label X, the one on top will be labeled Y, and we'll label this last one Z. The next step is to draw a line that is parallel to XZ and also goes through vertex Y, and that line is this red line up here. Next, label a point on that line, and we'll call that A. This way, when we want to refer to the red line, we can simply refer to it as the line that goes through AY. Next, we'll label this angle alpha, and we'll call this angle beta. An interesting side note about this construction is that the line that goes through vertex Y and is parallel to XC is unique by Euclid's parallel postulate. An interesting thing about the parallel postulate is that despite how intuitive it seems, nobody has actually been able to provide a concrete proof. Now to start off this proof, we're going to say that XY is a transversal across AY and XZ. Using this fact, we can say that angle X and alpha are alternate interior angles, which implies that angle X is equal to alpha. And similarly, we can say that angle Z is equal to beta. Now if you look at the top of the triangle, you can see that alpha, angle Y, and beta lie on a straight line. So this means that their sum is 180 degrees. Now using substitution, since alpha is equal to angle X and beta is equal to angle Z, we can say that angle X plus angle Y plus angle Z is equal to 180 degrees. And this concludes our proof.
Congruent triangles are two triangles with sides of the same length and angles of the same measure. More informally, they are the same shape and size. In order to prove two triangles are congruent, we need three equal values from a mix of sides and angles. The specifics of which combinations are acceptable will be covered in the Pons-Asinorum proof. These three value criteria are actually a theorem proved by Euclid from his postulates. Each criterion proof is dependent on assuming the other criteria to be true. In order to prove Morley's theorem, we're going to have to call on Pons-Asinorum. Pons-Asinorum tells us that the two base angles of an isosceles triangle are equal. We will prove this to be true using the side-angle-side congruence criterion, one of three congruence criteria for triangles, along with side-side-side, angle-angle-side, and angle-side-angle. Now wait a minute, did I not just say that there were three congruence criterion and then give a list of four? Viewer, where did I make a mistake here? Pause the video for a minute and think about it. Okay, so what conclusion did you come to? Ah, I see. So you're saying that angle-side-angle and angle-angle-side both include two angles, and by the previous proof, we know that three angles in a triangle add up to 180 degrees. Therefore, if two angles are equal for two triangles, then the third angle must be as well. So angle-angle-side and angle-side-angle are the same. Good job, viewer. Now on to the proof. What we have here is a triangle ABC and its mirror reflection triangle ACB. By construction, we can see that side AB on the left triangle is equal to side AC on the right triangle, and similarly, side AC on the left triangle is equal to side AB on the right triangle. And angle A is the same for both triangles. Therefore, these triangles satisfy our side-angle-side criterion and therefore are congruent. So angle B is equal to angle C.
Now that we have proven the necessary theorems, it's time to move on to the full proof of Morley's trisector theorem. The following is the statement of Morley's trisector theorem. First, take an arbitrary triangle and trisect each of its angles. To do this, you will need to draw two line segments originating from each origin, and these line segments should split each angle into 3 equal parts. Next, extend each of the angle trisectors until they meet at 3 points, as shown. Now, based on Morley's theorem, these 3 points will always form an equilateral triangle. And this picture here is the final result of Morley's trisector theorem. Now, before we move on to the full proof, let's talk about the man himself, Frank Morley.
Frank Morley was a man known for his math skills, but he was also a strong chess player. In fact, he once defeated the longest reigning chess world champion in history, Emanuel Lasker. Morley's theorem is simple to understand, but difficult to prove. That is why it is also known as Morley's miracle. However, our job was made much easier by John Conway. John Conway is an English mathematician who in 1995 presented the first recorded proof of what is now known as Conway's proof of Morley's theorem. This proof is considered to be the simplest proof of Morley's theorem, and it is a unique proof in that it is a proof via geometric construction.
The general idea of Conway's proof is to take an equilateral triangle and construct triangles around it, such that when pieced together, the original triangle will be formed. Now it's time to set up our construction. Let's let A, B, and C be the vertices of our original triangle. Now let's define the angles as shown. Let's let alpha be equal to angle A divided by 3, beta be equal to angle B divided by 3, and gamma be equal to C divided by 3. Now for example, alpha plus is equal to alpha plus 60 degrees. Alpha plus plus is equal to alpha plus 120 degrees. Essentially, if you see an addition sign in superscript, it implies that you add 60 degrees to the original angle. Using substitution and the 180 degree sum theorem, we can show that all constructed triangles are valid in this construction. For example, if you take a look at the top triangle, you can see that its angles are alpha, beta plus, and gamma plus. Alpha is equal to angle A divided by 3, beta plus is equal to angle B divided by 3 plus 60 degrees, and gamma plus is angle C divided by 3 plus 60 degrees. Now since A, B, and C are the vertices of our original triangle, their angles should add up to 180 degrees. Using this fact, we can show that alpha, beta plus, and gamma plus have a sum of 180 degrees. Now also in this construction, we need to set the bold lines to be equal in length to the sides of the equilateral triangle. If you want to be sure that our construction is valid, go ahead and pause the video, pick a triangle, and try to prove that its angles add up to 180 degrees. The next step in our construction is to fix the size and shape of the obtuse triangles. Let's focus on the right obtuse triangle. First, we need to add two lines such that the lines meet the long side of the triangle at an angle of beta plus. Next, we need to fix the size of the triangle such that each of the new lines are equal in length to a side of the equilateral triangle. This is where Pons-Asser norm comes into play. The converse of Pons-Asser norm dictates that the length of the lines will be equal since the base angles are made to be equal. Now, Jonathan will finish off the proof.
We want to prove that the two shaded triangles are congruent. We can see that they both have angles alpha and beta plus in common, along with the base side, which is equal to a side of the equilateral triangle in the center. Therefore, these adjacent triangles are congruent by angle side angle, and their adjacent sides are equal to each other. This process can be repeated 6 times to show that all adjacent edges in the figure are equal, and our 6 triangles will fit comfortably around our equilateral triangle. The only thing left to prove that our construction is valid is that the sum of our internal vertex is 360 degrees. We can see in this picture that one such vertex is constructed of angles gamma plus, beta plus plus, alpha plus, and 0 plus. That makes 5 pluses, which is the equivalent of 300 degrees. Then we would add gamma, beta, and alpha, which is equal to angle A plus angle B plus angle C divided by 3, which is 60 degrees. This gives us a total of 360 degrees. Similarly, all other internal vertices can be shown to have a sum of 360 degrees. Thus, our construction is valid. We have shown that our triangle constructed around the equilateral triangle is valid, and this process can be repeated for any arbitrary triangle and give us the same result of an equilateral triangle in the intersection of the trisectors. Amazing. It's a miracle. It's Morley's miracle. A special thank you to Dr. Akbar, the UTD campus, and all the geometers out there. Thank you for watching.